Okay, in this lecture we're going to look at four Vensim models for predator-prey, two models for predator-prey, one simple, one advanced, a model for epidemics and a model for catastrophe. So I'm going to start by looking at the very first one, the predator-prey simple model, which is the one that was covered in the lectures in class. And I'm going to fire up Vensim. I have a sort of pre-zoomed this model so it shows in the big screen, and I'll be toggling back. Let's take a look at this model here, and the first thing you'll notice is that it, like in the description that we did previously, it's got two stocks. It's got a predator population, and if you sort of hover over it, you'll see the units as foxes, and we're going to be looking at the unit and each of the dialog boxes in a second, but I wanted to go over first a little bit of the general structure. So you have a predator and a prey, and these are two stocks. Let's take a look at what goes into the predator. The predator has a birth rate, which we're calling predator net birth here in the model, and it's got a death rate defined by predator net death. There's an initial predator population, and there are rates of A and B that come into feeding the births and the deaths of the predator. Okay. Now the net birth of the predator, it's also dependent on the availability of prey. So you see an interaction between the population of the prey and the predator net birth, and we're going to take a look at how that looks mathematically in a second. And this is the same equation that we discussed previously in this lecture. If you look at the prey population, the prey population also has a net birth. It also has a net death, and the net birth population is driven by a constant C and by the availability of the prey, and the death of the prey is driven by a coefficient D and also by the availability of prey. Another distinction to make, again, is that the death of the prey is also driven by the availability of predator, meaning more predator, more death of prey. So that's essentially the Lotka-Volterra type interactions that we just discussed. So we'll go open in the dialog boxes. So let's start with the predator, and you'll see that the units, it's a level variable, so it's a control variable. It's a state variable, and it has units of foxes. Okay, and it's got its own equation here. Net birth minus net death. Okay, so it's fairly straightforward. It's got an initial value of initial predator, and if you click on initial predator, you will see it has units of foxes. It's a constant, and it's 100. Okay, so that's the initial value of the fox population. It's 100. Okay, let's move on to the net birth, and the net birth it's got units of foxes per year, and is found by multiplying the coefficient A times the population of predator times the population of prey. Okay, and so that's pretty straightforward. And if you go to the death of predator, it's simply the coefficient B multiplied by the predator availability, the population of predators. It's got units of foxes per year as well. And let's move on to the prey. Oh, wait, let's do A and B. A, it's the intrinsic growth rate of the foxes, and you can see here that it's got units. And I wanted to stop here at the units for a second, just to see how these are calculated. It's at the end it has units of 1 per year per rabbit, but it's essentially, so you know how it's calculated, it's the number of foxes born per year, per unit fox, so per unit fox present, and per unit rabbit. So that's how it works out, and it's got this value as we discussed previously. Okay, we can look at the coefficient B, and the coefficient B it's got units of 1 per year, but that's essentially the number of foxes per year that die per unit fox. Okay, and those are the units here. Very well. Now we can move to the prey equations, and again the net birth minus the net death will give you the population of prey. The prey it's got an initial value called initial prey. It's a state variable. It's got units of rabbits, and if we go to the initial prey, you will see the value there is 1,000 rabbits to start with. If you look at the net birth, it's essentially first order dynamics. It's the coefficient C times population of the prey. It's got units of rabbits per year. Okay, and if you look at the net death of prey, it's second order dynamics. It's the coefficient D multiplied by the population of predators, the population of prey. It's got units of rabbits per year. And you can see the values of C and D. Again, the growth of rabbits is simply units of inverse year, or rabbits per year per rabbits. And the coefficient D has units of rabbits per year per unit fox per unit rabbit. So it's second order dynamics. This is the value. Okay, so that's essentially the model setup. I wanted to show also something that it's key to look at. If you go to the model tab and go to settings, you can look at the settings of the model. And this model is run for 1,000 years, so from 0 to 1,000. The time step here, you can select it, but it's essentially I think we're going here at whatever 0.0078125 years is, and that's probably, I'm going to venture to say, see, this is 6 months, this is 3 months, this is a month and a half. So this is probably looking at the daily level, and I'm going to venture to say that. Please verify, just so we don't have to stop the video. All right, so we can do that, and so with this said, we can just, I'm going to zoom out of this so we can actually run the model. And okay, so this should do it. I'm going to actually fit it to screen. It's probably just as well. Okay. All right. So, and you can see that I've sort of pre-selected a couple of the plots, and we're going to see those. So I'm going to run the model, and just as is. And the model just ran, and then it shows a couple of graphs. I want to focus the attention. The graph here on the right is the one I had in the slides that I just showed, and I wanted to focus on this for a minute. And you can see, interestingly enough, and what I'm going to do now is I'm going to zoom into that, to this graph, so we can actually see it in detail. And so this graph shows the value of both populations, and I'll show you in a second how to generate these graphs as a custom graph. But essentially, what you have is it's what we said before, is that the predator population, which is in blue, and the prey population, which is in red. So these are the foxes, and these are the rabbits. Are oscillatory, okay, from the very beginning. So at time 0, you have 100 foxes and you've got 1,000 rabbits, and they start to interact. And then what you can see is this very interesting interaction in which, and at the very beginning, both species can grow. So the foxes can grow, and so can the rabbits. And what starts happening is that and they grow because they have an intrinsic growth. They can, there are rabbits available for the prey to grow, and rabbits have a natural way of reproducing, so they both grow. What starts happening is that as the foxes start getting more and more numerous, they start preying more and more on the rabbits, and then the rabbits start decreasing. Okay, and then you can see how the rabbit population takes a dive as as the foxes continue to grow because they just prey on the rabbits. What happens is that then the foxes start running out of rabbits to grow, and then if the rabbits drop too high, foxes are not going to be able to sustain the growth, and then the foxes start to drop. As the foxes start to drop because there's no rabbits, actually the rabbits start to recover because there's less predator, so that affects their growth, and they start growing. And then you start falling into the same dynamics. As the rabbits grow, then the foxes are able to pick up, and then again the same dynamics. Foxes grow too much, rabbits start running out, then foxes start running out, and then you have these sort of staggered, ups and downs for the foxes. And this is the cyclical, these sort of dynamic equilibrium that we refer to in class. Now, another plot that can be generated is the one I have here in the bottom, and I thought I'd show this. This is what's referred to as a phase portrait, and you can generate this plot by simply not plotting rabbits and foxes over time, but plotting actually rabbits and foxes together in the same plot. And what you get is this elongated shape. And if you think about what's happening here, is that each point in the two graphs, so let me toggle back here. The way that this plot is generated, just so you know, is that you can actually take every single time record, from 0 to 1,000. You have 1,000 data points. Each data point has a value for the population of foxes and a value for the population of rabbits. You can actually plot those two together, and what's generated is this phase portrait. And then what you can see is that it's this cyclical behavior, and what you have here is it's essentially an elongated shape that denotes sort of 4 areas. Okay, there is the first segment, which is a segment in which both the predator and the prey grow. Okay. And this is the phase in which they grow together. Both predator and prey are going up. What starts happening is that at some point the rabbits start to fall, even though the predators continue to grow. And that's this receding limb of the phase portrait. Then you get to a point where they both decrease. The foxes and the rabbits, both predator and prey, go down. So you were in this path. And then you get to a point where actually the rabbits start to grow, but the predator is still decreasing. Okay, and this is a cycle, and then the cycle is repeated again, and repeated again, and repeated again. Okay, so these oscillations up and down essentially reflect this phase portrait. I also wanted to show you something that I noticed when I did this model, is that if you go to the model settings and you decrease this, you go from you're not going to do it on a yearly basis. So let's do it every month and a half, or maybe every 6 weeks. Actually 3 weeks. Here, let's do that. Let's see what happens to this. And I'm gonna simulate this again, and I'll override it. I mean, you guys know this already. And I think one thing I'm going to do is that I'm going to zoom again back out to fit to screen, just so we can see. Now, it might be imperceptible, but you can see that these lines are a little bit thicker. It's that the resolution of the model, when it starts getting coarser, and let me actually make it even coarser. Let me go to 6 months, and run it again. Overwrite it, and you can see that the face portrait, it shows the cycle, and you can actually see where the cycle starts right there, and where the cycle ends. And let me zoom to that graph, just so we can see what's going on. You see, you now have essentially the start, and I'm not sure if this is the start or the end, but I would venture to say this is a start, and you have the sort of this spiral cycle. Now, of course, needless to say, the final resolution is more accurate. So this is really just to show the impact of the resolution on it. But if we go back to model settings and go back down to where we had it, or thereabouts, right there, do OK, rerun it, you can actually look at the face portrait again. Okay. See, again, and it's this nicely, tightly packed, cycle. So I thought it would be interesting and nice to see in this model. So with that said, I'm going to close this case, and we're going to move on to the next. Thanks for watching. So I'm going to stop the recording here.